In the previous video, we have seen why energy saving in distillation column is important and what are the various ways we can do that. One of the ways is for multi-component system is to have proper sequencing of the distillation column. But we had seen that if we want to, have sequencing of distillation systems, right, multi-component distillation systems, we encounter that as the number of product increases, your number of sequences also increases. Now there has to be some way out. So one of the ways is to do some analysis based on the vapor rate, as I discussed in the previous video, or there are other ways wherein the number of sequences can be possibly go down. One of the things which will reduce the number of sequences is adding some practical constraint. Like, theoretically there can be so many sequences possible, but practically we may not use all the sequences. The reason may be either safety or the reactive nature of the component, reactive or corrosive nature of the component, or maybe the component may tend to get thermally decomposed, or it may get to tend to have polymerization, or it is not easy to condense. So whenever there is a species which is hazardous in nature, we would like to remove that hazardous chemical as fast as possible, as soon as possible, naturally, with respect to its boiling point. So we will not appreciate, will not will not go with the sequences which take this hazardous species or hazardous chemicals till the last column. So we'll try to remove all these sequences wherein this kind of species is not removed at the earliest, or we would prefer the sequences where this kind of chemical is removed as soon as possible with its boiling point limitation. Same way, we have got some components which are highly reactive, some of them are highly heat sensitive, some of them are corrosive. So suppose there is a product which is a very reactive in nature, then you want to remove that product from the mixture as soon as possible, because otherwise if it remains in the mixture, it tends to get reacted away and the your conversion or your yield will go down. So you will try to remove that species as fast as possible. Same way, heat sensitive material, they will tend to get deteriorated if they are remaining in for a prolonged period in the mixture. Some of them are corrosive, so they'll corrode your entire pipeline if they are remaining in the mixture. So you'll try to remove them as fast as possible. Most of the times you'll try to keep your final product from the top only, because you would like to have it as pure as possible. And if it goes to the bottom, it may get decomposed because of high temperature. So these are all constraints which will limit or which will filter out number of sequences from very high number of possible sequence. So say for example, you've got 100 sequence which are possible, 129 or so which are possible. Out of that, 40 or 50 would be filtered out because of all such practical constraints, right? So that will reduce the number further. Now, based on this practical constraint, there are some general heuristics which have come down. So what are they? The first, remove corrosive or and reactive component first. Naturally, these heuristics will not be able to violate the basic principle of boiling point. Like if your corrosive component is third in as far as boiling point is concerned, you cannot remove from top in a first column, but you can remove that as soon as possible, maybe from second column. So your sequencing will start in such a way that you'll be able to remove that component as fast as you can. Try to get final product as distillate or vapor from the reboiler. Prefer direct sequence. Now this is again these heuristics, they are coming from the experience. So some of the heuristics can be explained, some of them have been observed by the people from year on year, and there may not be exact clarification or explanation for them, but people have experienced that this kind of behavior, this kind of process will ultimately give you benefit. Lump pairs of components with relative volatility is less than 1.1. That means if your separation is difficult, consider that mixture as one species, one pair, and take it to the last. Right? Don't separate them in the presence of other species. First, separate all other species and keep this particular, the most difficult separation to the last, so that your energy would be saved. And this can be separated, you may be using extractive distillation or azeotropic distillation or pressure swing distillation. So if there is a presence of other species, then it may impact the technology, right? There are certain, based on this, there are certain, other approaches which are also, heuristic, called heuristic approach. Remove the most plentiful component first. So if, in your mixture, if you have a very, if you have any particular species which is having very high amount, remove that first, because if you can remove that first, right, that will decrease the load on the further downstream columns. Remove the lightest component first, that is preferred direct sequence. Make splits with the highest recoveries last. So when you have highest recoveries, what I mean by highest recovery is that if you have got 100 moles of component B in the feed, and 99% are getting separated in column, in the distillate, so 99% is the recovery. So if the recovery is high, you require more energy or you require more reflux ratio. So try to do this at the end so that the presence of other species would not impact the energy, requirement of that column. Make the most difficult split last. This is also we discussed in the previous slide, that keep, any relative volatility which is less than 1.1, keep that last. Favor splits which give molar flow of distillate and bottoms with the smallest defects. So these are all the, heuristics which will, reduce the consumption of energy. So if I have 100 kilomole, try to have 50-50 splits. Now this is not exactly possible, so try to have 60-40, right? So try to favor the splits where your distillate and bottom are splitted almost 50-50. It all depends on your, feed composition. So it will not be exactly possible for you to devise 50-50 separation. So when we try to apply all these heuristics, we have to keep one thing in mind, that we cannot violate the basic fundamental rules of thermodynamics, of principles of the distillation column. However, we can try and approach this, which will help us to save the energy. And these are all heuristics which have come by experiences. Right. So let us say we have got one example, benzene, toluene, and ethyl benzene. This will clarify certain things, certain doubts in your mind which might have been created. So benzene is almost 270 kilomole per hour, toluene 282 kilomole per hour, and ethyl benzene 57 kilomole per hour. These are their alpha values, and these are the alpha adjacent. That is this upon this and this upon this. So if I want to separate this mixture, how do I go with? First, do the most difficult separation last. So in this, which is the most difficult separation, naturally 1.8 is not difficult, but if I compare it with 1.96, it is difficult. So I need to separate toluene and benzene last. First I need to separate benzene and toluene. Favor the direct sequence is also one of the, heuristics. So direct sequence means what? Separate benzene first, then toluene, and then ethyl benzene, right? So this gives direct. Large fraction component should be removed first. So which is the large component? Now as such, if you see, toluene is the large component, correct? But I cannot separate toluene in my first column. So what is the second large? Is benzene. So I separate benzene out of it, which again calls for a direct sequence. Favor equimolar sequence. So equimolar means what? As I told you, it should be 50-50. However, in this case, 50-50 is not possible. But if I separate 269 from top and 282 and 57 from bottom, it will make it at least 40-60. So that also calls for the direct sequence. So in this case, all the, four heuristics which I have shown here calls for the direct sequence, right? However, not all the problems are so simple to analyze, right? And hence there has to be some quantitative way. These are all qualitative discussions, right? So there has to be some quantitative way out, wherein I can say that, okay, if this particular value is less, my sequence is better. So for that, the method which calculates the vapor flow inside the column is suggested. So the separation scheme which requires minimum vapor boil-up rate is to be chosen, right? The calculation is based on very simple assumptions, and less vapor boil-up rate means less energy consumption. Let us try to see that. Why vapor rate? The vapor rate is decided as a factor is because it impacts both operating and capital cost. How does it impact operating cost? See, as your vapor requirement is more in the column, you require more reboiler duty. Then only you can generate more vapor. More reboiler duty means more condenser duty. Naturally, because the vapors which are going inside the distillation column needs to be condensed at top. So higher vapor rate means higher boil up rate and higher condensation rate. When you have higher boil-up rate, so heat duties in reboiler and condenser would be more. So this is nothing but your operating cost. Higher vapor rate means what? Vapors have a larger volume compared to liquids. So if you pump, if you feed in more vapor inside the column, that means your diameter will also be more. And higher duty, if I need to supply through condenser and reboiler, that means what? I have to provide larger area in the reboiler and condenser. So when my vapor rate is more, it not only impacts my operating cost, it also impacts capital cost. Other way around, if I can reduce vapor rate, I can reduce both operating as well as capital costing. So there is a method which was suggested by Porter and Momaho, and this is based on Underwood method. So we must have come across Fensky, Underwood Gilliland method for finding out minimum reflux ratio and minimum number of stages. There are certain assumptions which were provided into this particular equations, which will help you to find vapor flow rate of a given distillation column in an easier way. So this is a qualitative calculation. This cannot be quantified for a practical purpose, but still it will give you the qualitative way. So this is a distillation column where you add feed. This is the vapors going out, L and D. So we know that the ratio between actual to minimum is some factor. So reflux ratio, minimum reflux ratio multiplied by the factor 1.1 to 1.5 will give you actual reflux ratio. So I call that ratio as RF. Right? If I do the balance across this condenser, so V is equal to D into 1 plus RF into R minimum. RF into R minimum is nothing but by reflux ratio. So that will give me the vapor. Underwood equation is R for minimum reflux ratio is this 1 upon alpha minus 1 XDLK upon XFLK minus alpha into this. Now this can be further simplified because I am saying that there is no heavy key in distillate, right? XDHK term is 0. So I already said that it is a perfect separation. Only light key will go in top, no light key in bottom. Only heavy key in go in bottom, no heavy key in distillate. So if there is no heavy key in distillate, this term with 0. So my R minimum is 1 upon alpha minus 1 XDLK upon XFLK. But since light key is only given is coming here, FXFLK is equal to DXD XLDK, because there is nothing in terms of light key which is going in the bottom. So X, light key in bottom is 0. Since X light key in bottom is 0, plus BX would be 0 term. So FXF is equal to DXD, which I can replace here and I can write this as F by D. So my R minimum can be written as 1 upon alpha minus 1 F into D. So this can be replaced with 1 upon alpha minus 1 into F by D. And when I substitute D here, my equation becomes V into D plus F RF upon alpha minus 1. So this will give me the idea how can I calculate vapor rate, and we'll discuss more on this, how to use this to calculate vapor rate for a given sequence, right, in our next video. Thank you.